So Knuth-Morris-Pratt is a linear time algorithm. Surely we can't do better than that, can we? Well, it's not the end of the story. Now we're going to look at the Boyer-Moore algorithm. And it's also a very simple idea that's extremely effective in practice. So here's the idea. Instead of matching the pattern against the text, moving from left to right in both pattern and text, Boyer-Moore said, what if we try to scan the characters in the pattern from right to left? When we find a mismatch, we can skip, we know all the characters in the pattern. So for example, if we're looking for a needle in a haystack, if we first look at the last character in the pattern, which is an E, and we find that N in the text, then it's clear that the next possible match is when the N's lined up. Because if there's any other lineup, it'd be all these characters that we know are not N compared against N, so we might as well just move it so the N's are lined up. And that's good, but that's not as good as the next case. If we happen to run into a character that's not in the pattern, then we can just skip all the way over. We don't have to compare any of our pattern characters against that one. So we can just add M if we have M pattern characters. So then in this case, we have a more complicated situation. We match the E and we have a bunch of E's. And so part of the algorithm is to figure out when you do match a character that's in the pattern, what do you do? But the intuition is it's fast because you're often going to have this kind of case where you find a mismatch. And since you're going from right to left, it's you know that if there's a character in the text that's not in the pattern at all, you can shift over M characters at a time. And that's a huge win in a lot of practical situations. So how much do we skip? So the first case is clear. If there's if you run into a text character that's not in the pattern, then you just move I from wherever it was to one character beyond the current one that you're looking at. And that's an easy calculation. It's just incremented by the number of pattern characters that you've not looked at. Now, but if you have a character in the pattern, then you want to align the text N, in this case, with the rightmost pattern N, and that's pretty good. But you don't always want to do that. If you, for example, we have a mismatch on E, if you were to say, oh, let's line up on the rightmost E in the pattern, that would involve backup. So you don't want to do backup. In that case, you just move on by one. So there are times when the heuristic is no help. So what you really want to do is just increment by one in that case. So just given those basic preliminaries, it's clear that it's actually easy to go ahead and pre-compute how much you might want to skip. So you start out with -1. So this is the amount that you're going to increment the text pointer. And -1 means you just, if it's not in the patterns, you're just going to move on one. And so all you do is go through the pattern, and so let's start with N. So we want to fill in this table for N, and it says, so if we are going to find an N in the text, what do we want to do? We want to move to the next text character. We want to compare the next text character against this one, which is 0. So right of pat.caret j equals j, and that's going to fill in that 0. And then we go to j equals 1. For the E, E, D, L, it's the same. For what happens is if you do that for every letter in the pattern, if you have a letter that appears more often, it gets overwritten until the rightmost occurrence is the one that's there. So that pre-computation is just one pass through the pattern. And then given that pre-computation, then again, we're going to implement, this is an implementation of Boyer-Moore for using a for loop, incrementing the text character. And so we are going to have the text pointer I. In the course of the algorithm, we're going to compute a value skip, which is the amount that we're going to move the text character. So we go all the way through the pattern from right to left. If we get all the way through the pattern and we find a match and we don't change the value of skip, then we found a match. If we get all the way through the pattern, we don't find a mismatch. It's all matches. We don't change the value of skip, and we found a match. If we do find a mismatch, then we're going to compute the value that we skip, which is where we are minus that table, that thing that we computed, and that's the amount that we're going to add to the text character to take care of the mismatch for the right to left mismatch. And if it's always going to be at least one, but if this thing is negative, we're not going to back up. That's it. So it's a very simple implementation based on this idea of moving from right to left and skipping over the whole thing if we find a mismatch. And the key thing about Boyer-Moore, you can study that implementation and figure it out easily. But the key thing is that this mismatch character heuristic takes time proportional to n over m. That's kind of amazing. We had started out with a brute force, which was n times m, and then we got linear time. We're happy with n, but actually there's a lot of practical situations where you can do the search in n over m. The longer the pattern gets, the faster the search gets. It's not only sublinear, it gets better. That's kind of amazing. Now, there's a caveat there because there is a worst case that could be as bad as the brute force. So this is just an example of the worst case where you go from right to left and always get to the first character before finding the mismatch, and you can't do anything better than move over one. But actually what you can do is build something kind of like Knuth-Morris-Pratt to make sure that you don't do something like this with a repetitive pattern. And you can get the worst case to linear. But it's really of importance for intermediate length patterns because you're so often going to be able to get this n over m performance. And that's a widely used algorithm, the Boyer-Moore algorithm.